Welcome back to The Explainer. So for episode 3.1, I want you to imagine a modern ship not just as this massive static structure of steel, but as a living, breathing organism. Think about it. The hull is its skin, the engines are its muscles, and snaking through literally every single deck is this vast, pulsing circulatory system. But instead of just one single heart, this steel organism relies on dozens, even hundreds of mechanical hearts to survive. Today, we're focusing entirely on the critical machinery that keeps those vital fluids moving, pumps and pumping systems.
We're talking about over 100 pumps on a single vessel, all pulsing simultaneously. Some of these are tiny, right? Just moving a little trickle of lubricating oil to keep a bearing from completely melting down. But others are absolute giants, shifting tens of thousands of tons of seawater in a matter of hours just to keep the ship upright in heavy weather. And the stakes here are incredibly high. If an engineer picks the wrong pump type for a specific job, well, best case scenario, you've just wasted a bunch of money on poor efficiency. But the worst case, you literally cannot pump water out of a flooding compartment when it matters most, and that massive steel organism sinks.
So, here's our roadmap for today. First, we've got the ship's circulatory system. Then we'll meet the pump families, look at the very real threat of cavitation, compare bilge versus ballast systems, and finally, cover diagnosing the danger.
Section 2. Meet the pump families. Okay, let's dive into this mechanical taxonomy.
At its most fundamental level, what actually is a pump? Basically, it's just a device that adds energy to a fluid. It either physically moves that fluid from point A to point B, or it raises the fluid's pressure so it can do work. But you might be wondering, why do we need over 100 of them on board? Well, it's because no single pump design is perfectly efficient across every single combination of flow rate and pressure that a ship needs. Moving a few precise liters of thick, sludgy fuel oil requires a completely different mechanical approach than moving an absolute ocean of thin seawater. And that brings us to the three main pump families we've got outlined in this table. First up, displacement pumps. You can think of these as taking discrete gulps of fluid. A piston or a gear physically traps a fixed volume and just shoves it forward. Because they actively trap the fluid, they are self-priming and handle high-resistance, precise volume tasks perfectly. Next, we have the true workhorse of the ship, the centrifugal pump. Now, this doesn't take gulps. Instead, it uses a spinning impeller to literally fling the fluid outward using centrifugal force. It's incredibly efficient for general, high-volume transfer, but there's a catch. It needs to be primed, meaning it actually has to be full of liquid to start working. And finally, axial flow pumps. These act essentially like a propeller inside a pipe. They push huge volumes of fluid straight through at a very low pressure, which makes them absolutely ideal for things like circulating water through massive condensers.
Moving right along to Section 3, the threat of cavitation, or what happens when we push these fluid dynamics just a little too far.
This brings us to a really critical mathematical concept, net positive suction head, or NPSH. Simply put, this is the safety margin between the actual pressure at the pump's suction inlet and the fluid's vapor pressure at its current temperature. Mathematically speaking, the available NPSH is the suction pressure minus the vapor pressure divided by the fluid's density and gravity, usually measured in meters of liquid column. Now, every single pump has an NPSH required set by the manufacturer, while the physical system it's installed in dictates the NPS available. If that available NPSH drops below the required NPSH, well, disaster strikes.
Now, what's really interesting about this slide is this bizarre mini-mystery. How on earth can cold seawater suddenly start boiling inside a pump? Most of us are taught that boiling only happens when you crank up the heat, right? But liquids also boil when you drop the pressure. If a pump sucks too hard, the pressure inside drops so incredibly low that the cold water literally flashes into vapor.
Let's break that down using a really vivid analogy. Imagine trying to suck a super thick milkshake through a tiny narrow straw. If you suck too hard relative to what the straw can actually deliver, you don't get milkshake, do you? You just create a vacuum bubble in your mouth. Well, the pump impeller experiences exactly this. In step 1, a restricted suction line chokes the flow. In step 2, the pump suction creates an extreme pressure drop. And in step 3, vapor bubbles literally form in the water. But here's the crazy part. As those bubbles get flung outward to the higher pressure side of the impeller, they violently collapse. This bubble collapse is called cavitation, and those microjets of water are so intense they actually physically erode the solid metal of the impeller over time.
And while we're on the topic of vaporization, I need to issue a strict warning here about a totally invisible danger. If you ever run a centrifugal pump against a completely closed discharge valve, no fluid can leave the pump,
So the trapped fluid just endlessly recirculates around that spinning impeller, absorbing massive amounts of friction energy. It heats up incredibly fast, flashes to vapor, and will completely destroy the pump internally. And the scariest part, from the outside, the casing usually looks perfectly normal until it's too late.
Section 4. Bilge and ballast systems. Time to zoom out and look at the macro systems.
The two most crucial fluid networks on a ship are the bilge and ballast systems, and they honestly have completely opposing goals. The bilge system is all about pollution control. It's designed to collect those nasty, oily water mixtures that naturally pool up in the lowest, dirtiest spaces of the engine room and then safely process them. The ballast system, on the flip side, is entirely about structural stability. It moves massive amounts of clean seawater into and out of dedicated tanks to actively control the ship's trim, its list, and its overall stability out on the waves.
Now, because the bilge system handles oil, it operates under the absolute strictest international pollution laws, and the magic number here is 15. The absolute legal limit is 15 parts per million. Any bilge water discharged overboard cannot contain more than 15 parts per million of oil, period. This is heavily monitored by automatic equipment. Try bypassing the system or falsifying the records, and you are looking at multi-million-dollar fines and direct criminal liability. We're talking actual prison time for the engineers involved. It is no joke.
Conversely, the ballast system isn't really sweating over parts per million. It's worried about staggering volume. To put this in perspective, a single large centrifugal ballast pump on a bulk carrier might shift 2,000 to 3,000 cubic meters of water per hour. During a major cargo loading operation, these pumps will move tens of thousands of tons of water in less than a single day. If these pumps fail, the ship literally cannot safely load cargo, or even worse, it could completely lose stability in heavy weather.
Section 5. Diagnosing the danger. Let's move to and see how this builds into real-world sensory diagnostics.
Picture this. You're walking the floor plates of a loud, vibrating engine room. You pass by a massive centrifugal pump, and you suddenly hear this distinct, rattling, gravelly noise coming right from the casing. It almost sounds like a handful of marbles are just bouncing around inside it. You glance up at the discharge pressure gauge, and the needle is fluctuating wildly. Based on the knowledge we've just covered in this explainer, what is your very first suspicion?
If you instantly guessed cavitation, hit the nail on the head. That gravelly sound is the absolute classic acoustic signature of vapor bubbles violently collapsing against the impeller. It is your earliest and, honestly, your cheapest diagnostic tool. Before you jump to conclusions, assume the pump is mechanically shattered, and tear the whole thing apart, you need to immediately suspect insufficient net positive suction head. You'd want to check the suction strainer to see if some blockage is acting like that pinched milkshake straw. You'd verify the suction valve is actually fully open, and you'd double-check if the liquid level in the supply tank has dropped way too low.
Because ultimately, it really comes down to this. The right pump keeps the ship breathing, but poor suction will absolutely stop its heart. Whether it's rapidly shifting 3,000 tons of seawater to keep a massive vessel upright, or carefully, meticulously stripping an oily bilge to protect the ocean, these circulatory systems are the unsung lifelines of global shipping. So the next time you hear a pump running, ask yourself, do you actually know what's happening to the pressure inside? Have you listened to your systems today? Thanks so much for joining me for this explainer, and as always, keep your curiosity flowing.